Hello, my name is Desmond Edegesi, and I'll be taking us on the subject mathematics. In this class, we'll be looking at the theme numbers and numeration, and our topic for today is using logarithm in calculations for numbers greater than 1. We'll be carrying out exercises in this regard. So far, in our previous classes, we've learned how to make use of logarithm tables to find the logarithm of numbers. We also found out how to make use of the anti-logarithm tables to also find the anti-logarithms of numbers. Well, in this class, we'll be putting all of that knowledge to work. Let's go on into our class where we will see how we can apply this knowledge in practical examples of calculations. Follow me. Let's take this practical example. If you were asked to calculate the following using the logarithm table, 17.2 squared times 4.93 all over the cube root of 6,750,000. I guess it looks like a complex problem. Well, as we go into our class, we'll see how simple it really is. So to begin, we first lay out a table so that we can do our work in a neat manner. In your table, you should have a part for your number and a different part for the logarithm of your numbers. So quickly, we'll take our first number, which is 17.2 squared. To work on this, we would first find the logarithm of 17.2. Again, if we remember, we said to find the integer part of our logarithm, we would count the number of digits that we have in the integral part of our given number, which is 2 digits here. So we have 2 digits minus 1, and that would give us 1. It means that the logarithm of 17.2 would be 1 point a fractional part. That fractional part, we said, we would simply look it up from the logarithm table. Let's go ahead to look up our logarithm. So we have the first 2 digits of our number, 17, is looked up from our row. That is traced down. And then we have the third digit of our number, 2, which is looked up from our regular column here. If we trace 2 down to try and intercept our row, we'd have our intercept at this point. The number that we have at that intercept is what? 2, 3, 5, 5. Therefore, our logarithm number becomes 1.2355. Let's put that down in our table. So we have 1.2355. But take a look. We have our number 17.2 raised to a power 2. It simply means that the logarithm number that we have will be multiplied by 2. So if we multiplied this number, we'd have 0. Carry 1 over, we'd have 1. If we carried 1 over again, we'd have 7. Then we'll have 4. And then we'd have 2. So we have a value 2.4710. Once again, we'll take the next number we have here, which is 4.93. To find the logarithm of 4.93, we'll have our integral part as 1 digit over here minus 1. That would give us 0. It means that the logarithm of 4.93 would be 0. A fractional part. That fractional part again we will look up from our logarithm table to get our number. So we have the first 2 digits as 49 and the third digit as 3, which is traced again from our regular column in this section. If we trace that column down, it would intercept our row at this point. And that would give us 0.6928 as our value. It means therefore that the logarithm of 4.93 is 0.6928. Let's put that down again on our table. So far, we've been able to find logarithm numbers for our values here and here. Now, from the operator that we have between both values, it means from the product law of indices that we would add up our logarithm values. Let's do that quickly. So we have 2.4710 plus 0.6928. And that would give us 8, 3, 6, 1, and 3. So we have 3.1638. Finally, we have our value here to work with. And that value is the cube root of 6,750,000. We could write this value in a different way. Let's take a look. So we have 6,750,000. All of this raised to the power 1 over 3. This is just a different form of writing the cube root of 6,750,000. To find the logarithm of 6,750,000, once again we'll find the integral part of our logarithm to be how many digits do we have in the integral part of our given number? 1, 2, 3, 4, 5, 6, 7. It means that we would have 7 minus 1, which is 6. And it means that our logarithm number will be 6 point a particular fractional number. Now we have our integer part as 6 point a fractional part. To find the mantissa part of our logarithm, we would take our number here, that is the significant part of our numbers, which are 6, 7, and 5, and look it up from the logarithm table to get our mantissa. So again, we take the first 2 digits of our number, which is 67. We trace it down from the row 67. We also find the third digits, which is 5. 5 is looked up from our regular column within this section. It is traced down to intercept our row at that point. And at that point, we have a value 8293. It means, therefore, that the logarithm of 6,750,000 is 6.8293. So we put down our values in our table. 6.8293. But remember, we were asked to find the cube root of 6,750,000. And we have written it out here as the power 1 over 3 of 6,750,000. It means, therefore, that the logarithm of our number here will be multiplied by 1 over 3, which is just another way of saying this value, 6.8293, divided by 3. If we did our division here, we would have 2.2, 22 here would have 7, here would have 6, would have 4, and so on and so forth. We'll leave our number as 2.2764. If we look closely at our question here, we have our numerator part divided by our denominator. Under the laws of indices, which we call the quotient law in particular, the numerator would subtract our denominator to get a certain value. It means, therefore, that we will subtract 2.2764 from 3.1638. And if we did that, we would have 4, would have 7, would have 8, would have 8, I would have 0. So we have our value as 0.8874. But remember, this value is the logarithm of the number that we seek for. That is the number that we are required to find from our question. It therefore means that to get that number, we would need to find the anti-logarithm of 0.8874. To find our anti-logarithm, the integer part would be 0, which is our value here, the value of the integer of our number, plus 1, and that's 1. 1 indicates that we would have 1 digit before the decimal point in our final answer string. The fractional part, which we have as 0.8874, is found from our anti-logarithm table. Let's go and get that from our anti-logarithm table. So over here we have our anti-logarithm table. The first 2 digits, which we have as 0.88, is found on our row, traced down along the row, and then we find the third digit, which is 7, on our regular column here. If we trace that down to intercept the row, they would intercept at this point where we have a value 7709. The last digit on our number string is 4. 4 is looked up under the difference column. If we traced 4 down to intercept our row again, they would intercept at this point here where we have our value as 7. To get our anti-logarithm, we'll add up our values here and here. That is 7709 and 7. And that would give us 7716. So we have our final answer string as 7716. But remember, we had said that we have 1 digit before our decimal point. It means that we'll move our decimal point 1 step only to have our final answer as 7.716. Let's take a look at our second exercise here. We've been asked to calculate the following using the logarithm table, that is 29.86 times 105.2, all divided by 685.3. Once again, we simply lay out a neat table with fields, number, and logarithm. Then we'll take our individual numbers and work with them. So we have 29.86. We find the logarithm of 29.86 by first finding the integral part of our logarithm, and that would be 2 digits as seen on the integral part of our given number minus 1, which is 1. Therefore, it means that the logarithm of 29.86 would be 1 point, a fractional part. The fractional part we would look up from our logarithm table. Let's go to our logarithm table. So we have our table here where we will look up the first 2 digits of our number 29 on the row 29. If we trace that row down and also find the third digits on our number string 8 under our regular column here, if we did a trace down to intercept our row, they would intercept at this point where we have a value 4742. The last digit on our number string is 6. 6 is looked up under the difference column. If we trace 6 down, it will also intercept our row here. And at that point, we have a value 9. Our logarithm is gotten by adding up 4742, our value here, and 9. And that would give us 4751. So we have the logarithm of 29.86 as 1.4751. Let's put that down on our table. So we have 1.4751. Next, we'll work on our next number, which is 105.2. Again, to find the logarithm of 105.2, we'll get the integral part of our logarithm first by finding the number of digits on the integral part of our given number, which is 3 digits minus 1, and that would give us 2. It means that the logarithm of 105.2 is 2 points, a fractional part. The fractional part, again, we simply look up from our logarithm table. Let's go and do that. So we have the first 2 digits of our number string as 10. 10 is traced from the row 10. And the next digit we have on that number string is 5, which we trace down to intercept our row 10 at this point. At this point, we have a value 0, 2, 1, 2. The next digit we have on our number string is 2. 2 is found, of course, under the difference column. If we trace 2 down to intercept our row, they would intercept at this point where we have a value 8. To get our logarithm number, we'll add our values here and here. And that would give us 0212 plus 8, which becomes 0220. So we have the logarithm of 105.2 as 2.0220. Let's put that in our table also. Now we have a value for all of our numerator. We have the first value and we have the second value. But notice that we have an operator between the both of them, which is a multiplier. This operator implies, by the product law of indices, that our logarithm numbers will be added up to get a value. Let's add our values here. We have 1, 7, 9, 4. So we have 3.4971 as our value for our numerator. Now we have our denominator 685.3. We'll also find the logarithm of 685.3 by first considering the integral part of our logarithm. That would be 3 digits as seen on the integral part of our given number minus 1, which would give us 2, signifying that the logarithm of 685.3 would be 2 points, a fractional part. The fractional part we find by simply going to our logarithm table to find that. So once again, we have our logarithm table. We find the first 2 digits on the row 68. If we trace that down, and also find the third digit which we have here as 5. If we trace that down to intercept our row, we'll have an intercept at this point. And the value we have at that point is 8357. The last digit on our number string is 3. 3, of course, is found under the difference column. If we trace 3 down to intercept our row, they would intercept at this point where we have a value of 2. The logarithm of our number is found by summing up our value here and here, which would give us 8357 plus 2, and that is 8359. So the logarithm of 685.3 is 2.8359. Let's put that on our table. We'll have 2.8359. If we take a look at the question that was originally given to us, we had a numerator part and a denominator part. From the laws of indices, since we have a divider as our operator, it means that the denominator will be subtracted from our numerator. That is, their logarithms will be subtracted one from another. We'll subtract 2.8359 from 3.4971. Let's get our value here. That would be 2, 1, 6, 6. So we have 0.6612. This value 0.6612 is the logarithm of the number that we seek for. The number that answers our question asked at the beginning. It means that to get that number, we need to find the anti-logarithm of 0.6612. To find the anti-logarithm of 0.6612, we'll first find our fractional part of the number that we require to be 0. The 0 here is the value of the integer that we have in our given number plus 1, and that will give us 1. This 1 is not a value of itself, but an indicator that in the final answer string that we have, would have 1 digit before the decimal point. The fractional part of our number here is 0.6612. This value we will simply look up from the anti-logarithm table. Let's go and do that. So we have our anti-logarithm table. The first 2 digits of our number string is 0.66. Therefore, we look for the row 0.66 and do a trace down that row. Next, we find the 3rd digit in our number string, which is 1. If we traced 1 down from our column to meet our row, they would meet at this point. And at that point, we have the value 4581. So if we continue to trace our row down, and also find the last digit of our number string, which is 2, from the difference column, if we trace that column down to intercept our row, they would intercept at this point where we have a value 2. Our anti-logarithm is gotten by summing up our value here and here, and that is 4581 plus 2. So we have 4583 as our number string. So we have 4583. But remember, we said we have 1 digit before our decimal point. It means therefore that our decimal point would move 1 step. And therefore we have our answer as 4.583. And that's our final answer. Let's take a look at some more examples. If we are asked to calculate the following using logarithm tables, to do this, we'll quickly lay out our work in a neat table with 2 fields, number and logarithm. We'll take each individual number and work on them. So we have root 56.3. This could be written down in a different way as 56.3 raised to the power 1 over 2. To go on, we find the logarithm of 56.3. First, we get the integral part by determining that there are 2 digits in the integral part of our given number, and that means we subtract 1 to get 1. It means that the logarithm of 56.3 would be 1 point a fractional part. Our fractional part will look up from the logarithm table to get our number. So we have the first 2 digits of our number, 56, traced down along the row 56. We also find the 3rd digit of our number string 3 from our regular column here. If we trace our column down to meet with our row, The intercept of row and column would give us the number 7505. It means therefore that our logarithm is 1.7505. Let's put that down on our table. 1.7505. But remember that we have our number raised to the power 1 over 2. It means therefore that the logarithm that we found will be multiplied by 1 over 2, which is simply another way of saying 1.7505 divided by 2. If we worked this out, we would have 0.875, and so on. We'll leave our number like this. So we have 0.8752. Next, we take our second number, which is 39.5. To find the logarithm of 39.5 again, we take care of the integral part of our logarithm quickly, also by finding out the number of digits we have in the integral part of our given number. That's 2, subtracting 1 to get 1. It means that the logarithm of 39.5 is 1, point a fractional part. The fractional part is looked up from our logarithm table. So we have the first 2 digits again as 39. We trace our row 39 down and also find the third digit 5, which is looked up from our general column here. If we trace the column down to meet with our row, the intersection of row and column would give us the value 5966. It means that the logarithm of 39.5 is 1.5966. Let's put that down in our table. 1.5966. Next, we take care of our third number here, which is 8.64. To find the logarithm of 8.64, we'll take care of our integral part first by getting the number of digits in the integral part of our given number as 1. If we subtracted 1 from that, it would give us 0. It means that the logarithm of the number that we seek is 0. A fractional part. And that fractional part we simply look up from the logarithm table. Let's go and look up our fractional part. The first 2 digits of our given number is 86. So we go to the row 86 on our logarithm table and we trace it down. Next, we find the third digit of our number string from our column and trace it down to intercept our row to meet at this point where we have a value 9365. So we have our logarithm as 0.9365. Let's put this into our table. 9365. If we took a look at our original question, we will see that between each number we have an operator which are multipliers. It simply means by the product law of indices that we will add up all the values of our logarithm. Therefore, we'll add 0.8752 plus 1.5966 plus 0.9365. To get our value, let's quickly do our addition. We would have 3, 18, 20, 24. So we'd have 3.4083. as our summation. This value 3.4083 is the logarithm of the number that we seek for. That is, the number that answers our question here is therefore the anti-logarithm of 3.4083. To get our number, we need to find this anti-logarithm. To find this anti-logarithm, once again, we'll find our fractional part by getting the value that we have as the integral part of our number, that's 3, and adding 1 to that, which would give us 4. 4 is not a value of itself, but an indicator that in the final answer that we would have 4 digits before a decimal point. The mantissa that we have in our number here is 0.4083. This value we would simply look up from our anti-logarithm table. Let's go to look up our value there. So we have our anti-logarithm table. The first 2 digits on our number string is what? 0.40. If we traced along that row 0.40 down, and also find the 3rd digit of our number string, which is 8, under our regular column, and trace down our column to meet our row, they would meet at this point where we have a value 2559. The last digit on our number string is 3. Of course, our last digit is looked up under the difference column. If we traced our difference column down to meet our row, they would intercept at this point where we have a value of 2. So we have our value 2559 and the value 2. The anti-logarithm that we seek would be the summation of these values, and then will give us 2561. So our number string is 2561. Remember, we said that whatever number that we have as an answer would have 4 digits before the decimal point. Let's move our decimal point 1 step, therefore 2 step, 3 step, 4 steps. So we have 2561.0 as our number, which is simply equal to 2561 as our final answer. Next, let's look at the exercise here. We've been asked to find the cube root of 218 times 37.2 all over 95.43. Let's do this quickly by laying out again our table. So we have our first number 218. We're going to take each number one after the other. We'll find the logarithm of 218. First, we'll find the integral part of our logarithm as 3 digits. That is 3 digits from the integral part of our given number minus 1. And that would give us 2. It means that the logarithm of 218 would be 2 points, a fractional part. To get the fractional part, we'll look up our number from our logarithm table. So we have the first 2 digits of our logarithm as 21. And the other digit, which is 8, is traced from our column. If it is traced down to intercept the row, we would have a value as our intercept 3385. It means that the logarithm of our number 218 is 2.3385. Let's put this number down on our table. So next, we'll take care of our number 37.2. So find the logarithm of 37.2. Again, to get our integral part, we'll first find the number of digits that we have in the integral part of our given number, which is 2 digits minus 1, and that would give us 1. It means that the logarithm of 37.2 is 1 point a fractional part. The fractional part we will look up from our logarithm table shortly. So we have our logarithm table. The first 2 digits of our number is 37. So we find the row 37 and do a trace down that row. The next digit on our number string is 2, which we find under our regular column. If we trace 2 down to meet our row, we have our intercept of row and column, where we have the value 5705. It means therefore that the logarithm of 37.2 is 1.5705. Let's get this value into our table. Now we have values for both numbers in our numerator. From our operator, which is a multiplier here, this indicates that the product law of indices states that we will add the value of our log numbers. Therefore, if we added 2.3385, which is the value that we got for 218 as a log number, plus 1.5705, which is the value we got for the log number of 37.2, we would have 3.9090. 3.9090 therefore becomes the value that we get for our numerator in its log form. So we'll deal next with our denominator, which we have as 95.43. To find the logarithm of our number 95.43, we first find the integral part of our logarithm by counting the number of digits in the integral part of our given number. That number of digits is 2, so if we subtracted 1 from 2, we'd have 1. It means that the logarithm of 95.43 is 1 point a fractional part. Our fractional part is looked up from our logarithm table. Let's go to our logarithm table to look that up. So we have the logarithm table here. The first 2 digits of our number string is 95. Therefore, we go straight to the row 95 and do a trace down. We also find the third digit, which is 4, under our regular column here. If we trace that column down to meet with our row, would have an intercept at this point where we have a value 9795. The last digit on our number string is 3. 3 of course is looked up under the difference column. If we trace 3 down to intercept our row, they would intercept at this point to give us a value 1. To get our logarithm number, we add up our values here and here, and that would give us 9795 plus 1, which would give us 9796. That means that the logarithm of 95.43 is 1.9796. Let's write these values down in our table. Again, let's take a look at our original question here. If we notice, we have a numerator like we've said and a denominator. This indicates therefore from the quotient law of indices that the values of our log numbers will be subtracted one from another. Therefore, we would subtract 1.9796 from 3.9090. Let's do that quickly and let's see what we have. We have 4, 9, 2, 9. So we have our value as 1.9294. But remember, we seek to find the cube root of all the problem that we have managed to solve so far. Let us rewrite our problem in another form. So we would have 218 times 37.2 all over 95.43. All in brackets raised to a power 1 over 3. This form of our problem and the original form that we have is the same. It would help us also solve our problems in a more easier manner. So we already have all of this worked out to give us the value 1.9294. If we raise that to 1 over 3, it means therefore that we will multiply 1.9294, which is our value, by 1 over 3, which is another way of saying 1.9294 divided by 3. If we divided 1.9294 by 3, we would have 0.64331 and so on. Let's leave our number string like this. So we have our final number as 0.6431. 0.6431 as a value is the logarithm of the number that we seek as an answer to our question. It therefore means that to get this our number here, we need to find the anti-logarithm of 0.6431. To get the anti-logarithm, let's take the integral part. We'll get 0, which is the value of the integral part of our given number, plus 1. And that will give us 1. 1, of course, is not a value of itself, like we've explained, but it's an indicator that whatever our answer is would have 1 digit before the decimal point. Let's keep that at the back of our minds. Next, let's look at our mantissa part, which is 0.6431. This, of course, we look up directly from the anti-logarithm table. Let's go and look up our number. So we have the anti-logarithm table. The first 2 digits of our number string is what? 0.64. If we traced our row 0.64, and we also found the third digit 3 under our regular column here, if we trace that column to meet our row, they would intercept at this point where we have a value 4396. The last digit we have in our number string is 1. 1 is found under the difference column. If we trace our column down to meet with our row, we'd have an intercept of column and row at this point where we have a value 1. So our anti-logarithm is the summation of our number here and our number here. And that gives us 4396 plus 1. Therefore, we have our number as 4397. 4397. From the integral part which we calculated, we indicated that whatever our answer is would be 1 digit before its decimal point. Therefore, we move our decimal point 1 step here to have 4.397, and that is our final answer. Now, let's take a look at our final problem for our class here. So we were asked to find 49.23 cubed times 683.4 all over 182.5 squared times 83.8 raised to the power 1 over 3. Again, we'll simply lay out our table and take each individual number one after the other. So we have 49.23 cubed. To find the logarithm of 49.23, we'll get the integral part of our logarithm by finding the number of digits in the integral part of our given number. We have 2 digits, so we subtract 1, that will give us 1. It means that the logarithm of 49.23 is 1 point, a fractional number. That fractional number will simply go to our log table and look it up. Let's quickly do that. So we have 49.23, which we'll look up as the first 2 digits on the number string 49. Next, we'll go to the next digits on that string as 2. 2 is found, of course, under our regular column. If we trace the column down to intercept our row, they would meet at a point where we have the value 6920. The next digit on that number string is 3. 3, of course, is found under our difference column. If we once again traced our column to meet up with the row, they would intercept at this point where we have a value 3. So we get our log number by adding our values 6920 and 3, and that would give us 6923. It means that the logarithm of 49.23 is 1.6923. Let's write that down on our table. 1.6923. Now remember that our number is raised to a power 3. From the laws of indices, it means that we will multiply our log number by 3. And that would give us 9, 6, 27, 20, and 5. So we have 5.0769. Next, we take the next number, which is 683.4. To find the logarithm of 683.4, again, we take our integral part of our logarithm by counting the number of digits in the integral part of our given number. That's 3. So 3 minus 1 will give us 2. It means that the logarithm of 683.4 would be 2 points, a fractional part. A fractional part of our number is looked up from the logarithm table. Let's go and take a look. So once again, we have the first 2 digits as 68. If we trace along the row 68, and also get the 3rd digits from our regular column, if we traced our column to meet up with the row, they would intercept at this point where we have a value 8344. If we continue to trace our row down to also meet up with the last digits, which is 4. 4, of course, is found under our difference column. If we trace the column to meet up with the row, they would intercept at this point where we have the value 3. So to get the log number, we'll add up our values 8344 and 3, and that would give us 8347. It therefore means that the logarithm of 683.4 is 2.83 2.8347. Let's get this value into our table. We have 2.8347. If we noticed from our given question, we have a part of our question which is the numerator. We have the lower part, of course, which is the denominator. In our numerator, we have two sets of numbers. And so far, we've been able to find the logarithm of both sets of numbers. But notice that between our numbers, we have an operator which is a multiplier. This implies that from the product law of indices, the logarithm that we've found so far will be added up to get a sum. If we add, therefore, 5.0769 to 2.8347, that would give us what? That would give us 7.9116. That value is our numerator value. Let's go ahead to try to also find a value for our denominator. So once again, we'll take each number one after the other. We have 182.5 squared. To get the logarithm of 182.5, we'll first get the number of digits in the integral part of our given number as 3 digits. So if we subtracted 1 from 3, we would have 2. It means that the logarithm of 182.5 would start from 2 points and then would have a fractional part. So our logarithm will be 2 point something. To get that fractional part, we simply look up that value from our logarithm table. Let's go to our logarithm table. So once again, we have our number string with the first 2 digits as 18. Therefore, we look up the value 18 on the row 18. If we trace on the row 18 and also find the third digit on our number string 2, 2 of course is obtained under our regular column. If we trace 2 down to meet with our row, they would intercept at this point where we have a value 2601. The next digit on our number string is 5. 5 as the last number is found under the difference column. If we trace 5 down also to intercept our row, they would intercept at this point where we have a value 12. So, to get the logarithm of the number that we look for, we would add 2601 and 12. And that would give us 2613. Therefore, the logarithm of 182.5 is 2.2613. Let's get that down into our table. Once again, remember that our number is raised to a power 2. It therefore means that we'll multiply our log number by 2. And that would give us 6, 2, 2, 5, 4. So we have 4.5226. Next, we'll take the last number for our denominator as 83.8 raised to the power 1 over 3. To find the logarithm of 83.8, we'll first get the integral part of our logarithm by counting the number of digits in the integral part of our given number. That's 2 digits. If we subtracted 1, we would have 1. Therefore, it means that the logarithm of 83.8 would be 1 point a given fractional number. To get that fractional number, we simply look it up from the logarithm table. Let's go and do that. So we have the first two digits in our number as 83. 83 is found under the row 83, where we go further to trace down. We also find the third digit in our number string, that's 8. 8 is found under our regular column here. If we traced 8 down to intercept our row, they would meet at this point. And at this point, we have a value 9232. It therefore means that the logarithm of 83.8 is what? 1.9232. Let's get that down also into our table. Also notice that our number is raised to a power 1 over 3. It therefore means that the logarithm that we found just now would be multiplied by 1 over 3. 1.9232 multiplied by 1 over 3 is simply another way of saying 1.9232 divided by 3. So if we worked this out, we would have 0.641 0.6 and so on. To approximate this value, we would have 0.6411 instead. So we'll leave our value as 0.6411. Now also remember that the operator that we have between both numbers in our denominator is a multiplier, which implies that by the product law of indices, our logarithm values will be added up to get a sum. So let's add that up again, and this will give us 5.1637. So hooray! We have also a value for our denominator. If we take a closer look at our original question, we will see that our numerator here is divided by our denominator. It therefore implies that by the laws of indices, the quotient law of indices to be exact, whatever value we have as our log number here will subtract the value that we have as the log number of our denominator. Therefore, 7.9116 would subtract 5.1637, and that would give us this 6 minus 7 will give us 9. This would give us 7. This would give us 4. This would give us 7. And this would give us 2. So, if we subtracted 5.1637, which is our denominator, from 7.9116, which is our numerator, we would have the value 2.7479. This value, 2.7479, is the logarithm of the number that we seek for as the answer to our question here. It therefore means that to get our answer, we need to find the anti-logarithm of 2.7479. And to do that, we'll get the integral part first by taking the value of the integral part of our given number, which is 2. We add 1 to that to give us 3. This 3 indicates that whatever answer that we have would have 3 digits before our decimal point. Meanwhile, the mantissa part of our number here is 0.7479. This number, we simply look it up from the anti-logarithm table. Let's go ahead to look up our number. So we have our anti-logarithm table, and the first two digits of our number string is 0.74. Therefore, we go to the row 0.74 and do a trace down. The next digit on our number string is 7. 7 is found under our regular column within this section. If we did a trace down of that column to meet our row, they would have an intercept at this point. And the value we have there is 5585. The next digit we have in our number string is 9. 9, of course, being the last digit, is found under the difference column. If we traced our column down to meet our row, we would have an intercept of row and column at this point where we have our value as 12. It means therefore that our anti-logarithm would be the sum of 5585 and 12. And that would give us 5597. So we have our final number string as 5597. Remember, we said that whatever our answer be, we would have 3 digits before the decimal point in that answer. Therefore, let's trace our decimal points, moves 1 step, 2 step, 3 step. And so we have our 3 digits as 559, and of course, the answer we get is 559.7. We've come to the end of our class. Let's see if we can recount some of the points that we made along the course of our solutions. We said that in solving calculations using logarithms, for cases where we have multiplication, first, set out your solution neatly in a table that has headings number and log. Next, we said, find the logarithm of the numbers to be multiplied on separate rows and add them up by the laws of indices, which is said is a fundamental law that works in logarithm. We add up our logarithm numbers derived whenever we are working with a case of multiplication. Finally, in the third step, we said the sum that we get, we need to find the anti-logarithm in order to get the original answer that we seek. For cases of calculations where we have divisions, we said once again, just like the first, set out your solution in a table. Next, find the logarithm of the number that you seek to divide on separate rows and subtract them. From the laws of indices, the quotient law of indices to be exact, whenever we have cases of division, remember we said we subtract the powers. Finally, the anti-logarithm of the number that we get from our subtraction here is found. The anti-logarithm gives us our final answer. So find calculations involving powers. Once again, we set it out on the table, a neat table. Next, we find the logarithm of the number base that we are working with, and we multiply the value that we get by the value of our power. Next, we find the anti-logarithm of the number that we get, and hence we have our answer. For calculations involving roots, we said, again, of course, set out your answer in a neat table. Next, find the logarithm of the number base and divide that logarithm by the value of our root, that is the nth root. To get our final answer, we would find the anti-logarithm of whatever our value is from our calculation here. And that, of course, will give us a final answer. With all that we've managed to learn today, from the many exercises we took, I want to believe that after now, whenever we come across calculations that we have to make use of our logarithm knowledge, it shouldn't be a problem for us. It has been a pleasure for me once again being with you, and I look forward to having you in my next class. Bye for now. See you soon.